Hi everyone, my name is Ali, and today I'm going to present MatchFixAgent, language-agnostic, autonomous, repository-level code translation validation and repair. This work is a collaboration between University of Illinois, Amazon, and University of Oxford, and has been accepted at International Conference in Machine Learning 2026. So let's get started. In the beginning, I would like to discuss what is the problem of code translation. Code translation converts source code from one programming language to another. For instance, if you have this Java code here, which prints the numbers between 0 and 4 on the standard output, its equivalent translation in Python programming language is given here on the right. So why code translation is important? Code translation is important and it has applications in modernization where users use this in order to migrate their legacy software to more like cloud native applications. Existing techniques for doing translation involve transpiler techniques, tools like C to Rust, CXCO, and Java to C Sharp. So the good thing about these tools is that they produce more functionally correct code. However, the problem is that the generated code is pretty much not idiomatic and they do not generalize well across multiple languages. Recently, LLMs have excelled in this task. So we have like models like GPT and Claude, which they can do a good job. So they generalize well across multiple languages and they generate more natural code. However, the problem is that they do not scale to repository level code because of the size of the code bases and due to their like limited context window. So code translation was also featured in some news outlets. The most important one of them was from a statement from the White House, which was like appreciating everyone to use more memory safe languages like Rust. So let's look at some of the existing translation and validation techniques in the repository level. So for example, we have tools like AlphaTrans, which was published in FSC 2025. So AlphaTrans can only translate Java to Python, and it uses crawl VM for validation, actually for in isolation validation. We have Oxidizer, which was published in PLDI 2025. It can only translate Go to Rust, and it uses mocking for validation. Finally, we have Scale, which was also published in PLDI 2025, and it can translate Python to JavaScript, and it uses program execution for validation. So beyond the fact that we saw that they could only work for certain programming language pairs, for example, AlphaTrans was working only for Java to Python, let's look at some of the other like limitations here. So the first one is the generalization problem. So as I mentioned before, these tools, these existing tools which are published, they only work for certain language pairs, and there is a lot of high engineering overhead involved in trying to make them work for other languages. For example, as you can see here in the figure on the right, so Oxidizer performs dynamic analysis and it needs to capture all of the input-output cases from the Go code, and translate them to Rust. So imagine like extending this engineering effort to another language like C or C++. So you understand that the amount of work required to find a tool to capture this dynamic information for those languages. Another issue is that in Oxidizer, there is this idea of feature map. So a lot of design decisions are language specific. For example, the authors came up with a feature map which needs to be defined ahead of time before running Oxidizer. So errors should be mapped to anyhow error in Rust, and also variables should be mapped to lazy neo. And finally, there's this idea of type map in tools like Scale and AlphaTrans. So for AlphaTrans to work, there's this idea of a type map that should exist ahead of time, and we need to like for those specific languages map each specific type from the source language to the target language. And developing AlphaTrans, for example, took about 8 months. So part of this was developing that type map, which took a very long. So as you can see, the generalization is a big limitation. The second limitation is validation. So if you have like two translations, how can we say they're validated? So the problem with existing tools is that they rely on the available developer written tests in order to do validation. And the issue with those tests is that they can be incomplete and not rigorous. So let's look at this example here on the right. So we have a Go function which counts the number of characters in a given input. So for example, the corner case here is the emoji character. So the Go code returns 1. The translated Rust code by oxidizer uses the .len, and that returns 4 because the len function in Rust counts the number of bytes, not the characters. So this translation passes all checks in oxidizer because it was never tested on an emoji character. And we generated, in MatchFixAgent, we generated some test cases to expose this bug. And the correct translation should be using .chars.count, which is actually counting the true number of characters, regardless of the input type. Another problem with the existing tools is that, another problem with the existing test suites is that their code coverage can be very low because some developer-written tests do not necessarily test the entire code base. So code coverage is a big problem, and we will get to that later as well. Finally, the last limitation is program repair. So if you have a translation bug, what do we do with it? And the issue with existing tools is that they fail to repair translation bugs. So what they do is, for example, in AlphaTrans, they try to reprompt the fragments separately, which can actually potentially introduce new bugs. So what do we do in MatchFixAgent is that we create an LM agent and let it interact with an environment, give it some tools to execute some tests in order to make sure that no new bug is generated. All right, so all these limitations and challenges that we just discussed, in order to address them, we introduced MatchFixAgent. MatchFixAgent's architecture is shown in this slide. So for a given code base in the source language and a specific fragment from that source in the source language, and also a target code base and a target fragment, MatchFixAgent tries to give a verdict whether those source fragment and target fragments are equivalent or not equivalent to each other. So we only focus on functional equivalence here. And so MatchFixAgent has a modular design and it's interpretable because along with a verdict, it also generates some natural language reasoning on why it thinks that they are equivalent or not equivalent. And the idea behind MatchFixAgent is that we want to use LMs to do this approximation guided by program analysis in order to have some sense of soundness in the results. MatchFixAgent supports multiple programming languages, large language models, and CLI agents like Cloud Code and Codex. And we've done experiments in order to show this that it actually supports them. So let's look at the first component of MatchFixAgent, which is a semantic analyzer. So semantic analyzer performs 6 independent semantic analysis. So it basically tries to study the control flow of the source fragment and target fragment, the data flow of the source fragment and target fragment, and input outputs, library equivalence, exceptions, and also specification analysis. And each one of these analyses gives from their own perspective, a verdict whether the two fragments are equivalent, not equivalent to each other, and are basically accompanied with a reasoning. And so control flow and data flow analysis are more like a structural analysis, and IO and library equivalence are more like non-structural analysis of source and target fragments. So the idea here is that we try to do this analysis in a one-shot LM call and collect them and then pass them to an agent. So far, there's no agent involved in this pipeline. And then, so as I mentioned, all these analyses are combined and passed to a test generator and repair agent. And the idea there is to generate tests in source and target language. So let me explain them better in the next slide. So the test generator and repair agent is most probably the most important component because in here, we don't argue or reason about code statically, but we also try to execute tests in order to show equivalence or non-equivalence. So remember we had 6 semantic analysis. So the idea is to pass them to a test generator agent. And the job of this agent is to generate tests in source and target language. For example, if our source language was Java, this agent generates native JUnit tests, and if our target language was Python, it generates native PyTest tests. And these tests, the idea is to make them integratable later with the code base so that developers can actually use them. And then, so basically these generated tests are then executed and their outputs are compared to each other. And there could be two possibilities. So if the outputs are matching with each other, basically the test generator and repair agent terminates. If they're not equal to each other, a repair agent enters the loop and tries to interact with the code base, fixes the bugs based on the feedback that it got from test execution, and then the tests are re-executed until they produce similar outputs, or we reach the timeout. So to evaluate MatchFixAgent, we collected all of the benchmarks from 4 existing tools. So those include Oxidizer, Rust RepoTrans, AlphaTrans, and Scale. And this gave us about 6 language pairs. And from all these tools, we collected about 2,219 fragments. So these are pairs of source and target fragments in which we want to determine validation verdict. And these fragments came from code bases, and the size of those code bases are pretty big, so almost 1 million lines of code, and the test coverage of them were about 90%. So the first research question that we were interested in studying was definitely the translation validation. So how good is MatchFixAgent or existing tools in translation validation? So in here, as you can see, the super column tool validation shows 3 subcolumns: equivalent, not equivalent, and validation failure. So validation failure is the scenario where a tool, whether it's MatchFixAgent or non-agentic approach like AlphaTrans, they cannot generate a proper verdict. They cannot determine whether those source and target fragments are equivalent or not equivalent. So we put them, in order to make our categorization more flexible, we have this validation failure category. And as you can see, AlphaTrans is the one with the highest validation failure of about 43%. So on average, as you can see, 51% of fragments by existing tools have a verdict of equivalent, 20% not equivalent, and 28% is basically validation failure. So that 28% is actually a very high number, because almost 1/3 of the data set do not get any verdict. So in contrast, MatchFixAgent, it actually does a good job. So it can validate 99.2% of fragments. Only 0.8% of them cannot be validated. And so for 99.2% of them, we collect all those verdicts, and we basically compute an agreement score. So agreement is basically whenever MatchFixAgent and the existing tools agree with each other on a verdict. And on average, 72.8% of verdicts generated by MatchFixAgent agrees with existing techniques. So what happens when we have a disagreement, right? So disagreements can happen. For example, we can have false positive, false negatives. And in here, the disagreement is basically, for example, AlphaTrans says something is equivalent, but MatchFixAgent is something that says that they're not equivalent. So that's a dispute. So in order to better understand disputes and who is saying the right thing, we created a sample of about 145 cases across all tools. And we had 2 human investigators and who tried to do manual investigation, a human study on these samples. And at the end of the day, we found out that about 60.7% of those dispute cases actually resolve in favor of MatchFixAgent. So that shows the superiority of MatchFixAgent in terms of translation validation. So all these experiments and the results shown in this table were done with the Claude 3.7 Sonnet model. We also, in order to show the adaptability of our tool, MatchFixAgent, with open source models, Qwen3. So we did do all these experiments, and basically please refer to our paper for more analysis about cost and also the effectiveness in translation validation with an open source model. So on average, it's an order of magnitude over 20 times cheaper to use a Qwen3 model, and the results are very close to each other in terms of at least the agreement scores, 72.8% compared to 74%. So yeah, so basically open source models also do a good job in terms of translation validation. So the next research question that we had in mind was translation repair. So how good is MatchFixAgent if there is a translation bug? How good is it in terms of repairing it? To do this experiment, we collected 265 samples to do translation repair. And these 265 samples is basically the samples in which MatchFixAgent and also the existing tools like Oxidizer, AlphaTrans, they generated a patch as well in order to have a fair comparison. So out of these 265 samples, MatchFixAgent was able to fix 134 of them, about 50.6% success rate in terms of translation repair. And existing tools, as we mentioned before, they have a hard time fixing translation bugs, so only 18.5% of them were fixed. So MatchFixAgent fixes about 32% more translation bugs compared to existing tools. And remember when we mentioned that MatchFixAgent generates native tests in source and target languages? So, and one limitation with existing test suites was that they had low coverage. So on average, MatchFixAgent can help increase the code coverage by about 8.5%. And these generated tests can be actually used by developers of that they take basically the translated code base, and they can also take advantage of these generated tests with a higher coverage in order to better test their code base. So here's an illustrative example of how MatchFixAgent works. So remember that we had that emoji, the length of the number of characters example in the first place in the beginning of our presentation. So in here, the Go code actually extracts the number of characters from a string 1 and a string 2. And the Rust code originally was calling that .len method call here for capturing it. But remember that in the Rust, that captures the number of bytes, not characters. And if we had, for example, an emoji, that would actually not work. So here is the actual natural language reasoning generated by MatchFixAgent. So whenever it argues about incorrectness, here is the actual natural language text. As you can see here, it argues that the .len counts the number of bytes, not characters. And in order to do this the proper way, we have to use .chars.count. So in reality, in the experiments, the repair agent goes ahead and changes those .len calls to .chars.count. And at the bottom, you see the test generated by MatchFixAgent to expose this incorrectness. So this is basically MatchFixAgent in action. So the development cost and adaptability of MatchFixAgent was another research question that we wanted to study. So existing tools, they work only for one programming language pair for validating the translation across one pair, and they cannot be extended to more languages. Well, theoretically they can be, but it requires a lot of engineering effort. And as you can see, MatchFixAgent in terms of lines of code is only 1,650 lines, as opposed to, for example, Oxidizer, which is 19,000 lines of code. And here's also the adaptability with other CLI agents. So we repeated the experiments with Codex on a sample of 100 examples, and these Venn diagrams show the intersection between the agreement of verdicts between existing tools, Cloud Code, and also the Codex CLI agent. So in order to justify the design of MatchFixAgent, we performed two ablation studies. In the first one, we removed the semantic analyzer and the test generator agent. And in order to see the effectiveness of MatchFixAgent, so we removed those two main components. So that basically gives us a baseline agent. It's basically just one Cloud Code initiated with an initial prompt. And as you can see, as the size of the code base increases in terms of lines of code, so we have, for example, Iceberg Java and Crypto Java, the accuracy of the baseline agent decreases significantly by, on average, about 57.7%. But for example, the lowest, it can go to 25%. So basically MatchFixAgent, with the help of semantic analyzer and test generator agent, it does a good job in terms of translation, validation, and repair. So this was the first ablation study. which we removed two components. And then in our second ablation study, we only removed the semantic analyzer component, but we keep the test generator agent and repair agent. So basically, our idea for including the semantic analyzer is to reduce the cost of orientation phase of an agent. So agents, when they are initiated, they spend a lot of time in terms of orienting themselves into the code base, understanding what is expected of them, what they're supposed to do, and basically analyzing the code base. So we believe that having a semantic analyzer and passing those 6 semantic analysis will help reduce the cost significantly. So as you can see here, if we have, for example, MatchFixAgent without semantic analyzer and with the semantic analyzer, we will have about 4% less turns. So without the semantic analyzer, MatchFixAgent will have 4% more turns. This is because those 6 analyses are not done, and the agent needs to go and explore the code base by itself. And more agent turns means more token consumption. So we have about 6% more input tokens consumed and 4% more output tokens generated. And as you can expect, more tokens generated, it means that there will be more cost and time. So we will, MatchFixAgent spends about 7.5% more time without the semantic analyzer, and it is about 40% less accurate. So the accuracy drops and the cost increases. So this basically shows the importance of having the semantic analyzer in MatchFixAgent. So to wrap up, in this work, we introduced MatchFixAgent, a language-agnostic autonomous system for repository-level code translation, validation, and repair. We evaluated MatchFixAgent on 6 PL pairs and compared it with 4 tools. And the results show that MatchFixAgent can validate 99.2% of translations, and it can repair 50.6% of translation bugs. We did a human study to resolve, basically our human study resolved 60.7% of dispute cases between existing tools and MatchFixAgent in favor of MatchFixAgent, and we performed 2 ablation studies to justify the design of MatchFixAgent. So for more details about experiments, please refer to our paper on arXiv. You can also check out our artifacts on GitHub. Everything is open sourced. And yeah, so you can also basically scan this QR code to reach to our full paper on arXiv. Thank you very much.